All right, let's get started. I guess I was around December of 2011, I think, where I was doing what I always do. After I finish grading a stack of papers, I always grade a stack of papers in the order in which the students hand the papers in. And then I sit there and in a very primitive manner, I put them in alphabetical order. And so, I mean, I just sit there with the stack here, and then I take the first page off, the first paper, and whatever student name that is, that's here. And then the next one, I see, well, does that one go above or below this one? And so on. I keep doing that. And it turned out that in a stack of 25 exams, the first 6 were all in correct alphabetical order, which I thought was remarkable. And I sat there and thought, I wonder how likely it was that that happened. And then I started asking even more general questions, because that was nice that they were all in alphabetical order, but that would have been just as nice if they were in reverse alphabetical order. And it would have been almost as nice if I just didn't have to. It really bugs me as if I'm about 10 exams into the sorting process, and I haven't, and then all of a sudden, I get a name like Miller, and it's like, well, I got to put that in the middle here, and so I started asking questions related to that. So I came up with this project, and waiting for a student to come along, and not too long after I came up with this idea, Katelin Weiers decided that she'd like to work on this project. So I'd like to introduce Katelin, and she'll be talking about applying probability theory to alphabetical order.
So, as Dr. Katelin mentioned, here is the motivation behind my research this semester. He is grading the exams and trying to put them in alphabetical order. So we have the stack of papers, and we're going to take that stack and now create a new one where they're already in alphabetical order. So he kind of touched on how that would work, but that was the procedure, and looking at the probability that the first few were already in order. And then after that, I extended it on to the question of insertions, which I'll talk more about in the presentation. But looking at it mathematically, my ultimate goal is to define a formula for this specific type of alphabetical ordering. So the type that involved no insertions into the middle of the stack. So looking at it mathematically, you have a stack of n papers, and what is the probability that the first r of them are already in alphabetical order? And then after that, the question of if you have that same stack of n papers, what is the probability that you can put the first r in order without having to insert any into the middle of the stack? So to answer the initial question, I started looking at small samples, and one of the things you should know in probability theory is that the total ways to number n things is n factorial. So that's one thing I'll be using in my probabilities. But I started looking at samples of size 3, 4, 5, 6, just smaller samples that I could analyze and kind of count up the number of ways this was possible. So here you have the data set for n equals 3, so 3 papers that were handed in. And as I was doing my research, I looked at letters of the alphabet. Just makes it a little bit easier to kind of understand the relationships that are going on. So the probability that these letters are in alphabetical order is how I'm going to be looking at the different questions. But if you have 3 letters, the probability that the first 2 are in alphabetical order are the bold ones here. So you can have A, B, A, C, or B, C. Those would be the 3 possibilities. So the probability that 2 out of the first 2 in that series of 3 are in alphabetical order is 3 divided by the total possible 3 factorial, which simplifies to 1/2. And then I also looked at the case where n equals 4, and for the probability of the first 2 from that stack were in alphabetical order was the 12 divided by 4 factorial, which again reduced to 1/2. So as I started looking at all these different sizes of stacks, looking at the different number you could pull from the stack to put in alphabetical order, I realized that it didn't depend on the size of the initial stack. It actually only depends on how many you're considering. So you might start with 50 papers, you might start with 100, but if you're looking at the probability the first 5 are in order, that's going to be the same regardless of the size stack you start with. So that's kind of one of the basic results that I stumbled upon pretty early in my research, but for the rest of it, we can just look at the sample that we're considering, so just those first 5, we don't have to worry about the size of the total sample they came from. So based on this, came up with the conjecture that the probability that the first r are in alphabetical order is 1 divided by r factorial. And just the structure of the proof of how this works is that if you have a set of n distinct objects that can be put into alphabetical order, and you choose r of them, the total number of ways that those r can be in order is r factorial. So those are the total possible permutations. And of these r factorial permutations, only one of them is going to be in alphabetical order. It has to, there's only one way to alphabetize something. It has to just follow A, B, C, D in that order. So probability is the total number of outcomes in our event divided by the total of the sample space, which is the 1 divided by r factorial. So this is kind of the basic question that I started with. And then after this, I moved on to the question. First, I'll show you here just the direct application, like Dr. Phil mentioned. If you have a stack of 25 exams and you want to know the probability the first 6 are in alphabetical order, you can just take 1 divided by 6 factorial, which is about 0.0014. And then you can also look at the probability the first 6 are in alphabetical or reverse alphabetical order, which is a pretty simple question because there's only one way for it also to be in reverse alphabetical order. So you just add the two together and the probability of that is 0.00278. So again, the size of our initial stack doesn't matter. We could have started with however many papers we wanted. So now moving on to where I spent most of my research was with this idea of insertions. So just kind of an illustration of how that worked. If the first student's name was Baker, that's the name we're starting with. And if the student's paper gets turned in that comes alphabetically before that, we just place it on top, such as Anderson. And if it comes after it, like Smith, we place it on the bottom. So it's pretty easy to put those in order. But then names such as Jones or Miller or something that comes in the middle of the alphabet has to get inserted in the middle of the stack. And that obviously takes more time. And if you have a really large stack, it can be pretty difficult to figure out where it goes in the middle of your stack. So again, just starting off looking for different patterns with small sets of data, I created a computer program that printed out all these permutations so that I wouldn't have to try to come up with them all myself. Cases where n equaled 3, 4, 5, or 6, so that was the size of the sample that I was looking at. And the question of the probability of the first r can be ordered without any insertions. And it was pretty quickly realized that analogous to the first case, it didn't depend on the initial size n, only on those r we were considering. So we can just look at the case where n equals r in these smaller samples. So here are the permutations for r equals 3, which we kind of looked at with alphabetizing, but now we're looking at the number of ways we can arrange them without any insertions for all 3 letters. So you can see the highlighted ones here are the ways to do that without any insertions. So alphabetically, you can have A, B, C, or reverse alphabetically here. And then we also add now new cases in the middle where if you start with the middle letter B, you can put one on top and one on the bottom without having to insert anything in the middle. And then here's the case where r equals 4. Again, you have the alphabetical order and reverse alphabetical order are the two kind of extremes in the list. And then in the middle, we have the different ways that can start with the middle cases. So as I looked at this, I also looked at the cases for r equals 5 and 6 and trying to come up with patterns and seeing how this related, if there was kind of a formula we could come up with for these insertions. And as I looked at it, what I realized was that an interesting relationship was developing. So just kind of to summarize here, for the case where r equaled 3, you saw there were 4 ways possible without any insertions. And then for the case where r equals 4, there were 8. And then those were the number of ways possible for 5 and 6. And the last column there is just the probability by dividing by r factorial. Those are the probabilities for each sample size. And based on this, I came up with a conjecture that the total number of ways to order something without any insertions is actually 2 to the r minus 1. And that just comes from the middle column there. So in r equals 3, you have 2 squared or 4, and it follows for the cases that I looked at. So that was my initial conjecture. And then for the probability, simply dividing by r factorial. So back to our initial case where r equaled 3, the way I kind of analyzed the data was looking at how many ways possible started with each letter. So when you have the first letter A, there was 1 way, and the last letter C, there was 1 way. And that's always going to be true because when you start with the first letter in the set, you have to follow alphabetically. You can't skip anything, otherwise you're going to have to insert one in the middle. So when you're looking at the end cases, it's always going to be 1 way without any insertions. And then in the middle for r equals 3, we have 2 possibilities without insertions. And then if you recall from when r equaled 4, it was one way that started with A and one way that started with D, so the two ends again were one way. But then the middle cases both had 3 possibilities. So as I looked at these cases for r equals 3, 4, 5, and 6, an interesting relationship developed, which I hadn't really expected, and that was Pascal's triangle. And the way you look at it is each number represents the total number of ways without any insertions for each case. So I didn't really look at r equals 1 and 2 because those are pretty basic cases. You can obviously only do it one way. But then starting with r equals 3, you had one way to start with the letter A, 2 ways with the letter B, and 1 way with the letter C. And then same for r equals 4, it was 1 way with the letter A, 3 with B, 3 with C, and 1 with D. And the same was true for r equals 5 and 6. It just kept following this relationship, which based on this, once I kind of discovered that that was working, came up with the idea of looking at this recursively, proof by induction, just kind of showing that if we know it's true for the nth case, we can show it's also true for the case where n plus 1. So I'm not going to go into the details of it here, but I do want to show you an example of how this is working so you can understand kind of the logic behind the research and the formula that I did come up with. So basically when you're trying to count how many ways there are to do this, you can establish your starting letter, which here we're looking at the case where r equals 3. So it can start with A, B, or C. There's always one way that starts with the first letter and one way that starts with the last letter. But then when you have the case of the middle letter, it gets a little more complex because it's obviously not just one way anymore. So what you do is when you're looking at the middle letters, you have to remember that the letter that comes after it has to follow directly after it in the alphabet. So you can't go from B to D, for example, because otherwise you're going to have to insert something in the middle later on. So that doesn't really matter in the case where r equals 3, but it will matter later on. So B can either be followed by A or by C, which you see over there. And once you have that, it actually, once you establish your starting letters, you can move into a two-letter problem. So instead of looking at all 3, now we're only considering 2 letters. So we can renumber these letters. You can say that the A is 1 and the C is 2. So now it's a question of how many ways can you arrange 2 letters without any insertions instead of 3. And you can kind of think of it as like the B and the A are kind of becoming fused together. You can't have any gaps in between them. So now you're only looking at these 2 different letters and how many ways they can be arranged without any insertions. And the way to look at this is, so you have 2 letters now, A and C. So how many ways are there without any insertions in a series of 2 that start with the first letter, and that's 1. And then how many ways are there in a series of 2 that start with the second letter, and that's also 1. And that row of the triangle, and just that kind of recursive idea. So then you can add those together, and that's how you get the 2 kind of in the middle of the number of ways for the middle letter to be arranged without any insertions. And also, a little more complex here, but just to show that the idea does hold. For the case where r equals 4, we have 1 way for the first letter, 1 way for the last letter again. So just that basic idea of alphabetical or reverse alphabetical order. But then the middle cases are a little bit more complex because we have a couple of different options. So like I mentioned before, you can't go directly from B to D because you're going to have to insert in the middle then. So B can either be followed by A or by C. And once you do that, once you establish what letters can come next, it becomes a 3-letter problem instead of the total 4. So we renumber these letters. So now we have A is 1, C is actually 2, and D is 3. So it's a 3-letter problem. And then you can look at how many ways can you arrange these 3 letters without any insertions. That start with the first letter would be 1 from the last slides that we looked at. And then how many ways that start with the second letter in a series of 3, and that's 2 without any insertions. So you sum them together, that's how you get the 3 for B, and the same thing happens with C, although now you're starting with either the second or third letter in that series of 3. So it's the recursive relationship and summing them together based on the binomial coefficient identities, just following through Pascal's triangle, and that's how you get the case for r equals 4. So then just kind of a final comparison, if you had that initial stack of 25 exams, looking at the first 6 of them, as we said, the probability the first 6 were in alphabetical order was the 1 divided by 6 factorial. Then the probability, now we can look at, based on my research and my formula, that the first 6 can be placed in alphabetical order without any insertions. It's actually 2 to the r minus 1 divided by r factorial, which for this case of 6 papers translates into about a 0.0444 probability. So we're considering the case of alphabetical order and reverse alphabetical order, but now we have all these additional possibilities as well. So that is what I spent my semester researching on. There are additional possibilities to research with this, such as kind of looking into how many ways you can arrange them with only having to insert toward the top and bottom of the stack, because that would be easier than trying to find a way to insert into the middle. But this was what I worked on this semester, and that's the formula that I was able to develop. So.
Are there any questions?
So does this have much application to like programming? Like, is it a new technique that will help, or should we just stick with the old methods?
No, I'm really not very knowledgeable about programming and different techniques like that, but I would assume that this is something that could be extended to different cases. I just looked at it out the passing list of names, but it's an idea that could be extended into other cases as well. And I know that Pascal's triangle does relate to a lot of different areas, so it's interesting that this relationship did emerge on something that we weren't expecting when I started my research to kind of find that. So I'm not sure, but that would be an area of future research as well.
Do you know if there's any other research related to this kind of probability of ordering?
Yeah, I have not heard any, and I know Dr. Phil talked to the math faculty here, and they weren't sure based on a specific idea, but I do know that alphabetical ordering that is a common area of research with just ordering and probability and counting different aspects like that, but as far as I know, there have never been questions addressed about these ideas of insertions or anything of that nature.
Thank you all for coming.